Welcome back, anatomy students. We are now going to explore how the ECGs correspond to myocardial contraction. So I've got a description up here in yellow that is telling you exactly what's happening in the various chambers. I have a picture that is showing us what's going on as well. So the orange arrows are going to show us the direction of propagation of the electrical signal. And then you're going to see the ECG trace grow as we go from one picture to the next. So here we go. When we get the signal from the SA node and it spreads to the various cells in the atria are going to depolarize. And that signal, as you can see in red, is starting to spread here throughout our atria. And on the ECG, that's what the P wave is, the first little wave that we have here at the bottom. Next, we have the atrial depolarization is complete, and that is going to be this tiny segment that exists between the P wave and the QRS complex. And so now you can see in our picture, the atria are all red. Depolarization is now complete. Next, in number 3, we have ventricular depolarization. And so that's where we get the front half of our QRX complex, or, the very recognizable spike that happens right in the middle of the ECG. And what is happening here is that our signal has traveled from the AV node to the AV bundle, down the right and left bundle branches, and out and around the walls of the ventricles via the Purkinje fibers. So all of that is happening again very, very quickly because those cardiomyocytes have so many gap junctions in between that they are able to spread ions extremely quickly. Notice that our atria have now turned green. They are repolarizing during this time. Now we have ventricular depolarization is complete. That's going to be the second half of our QRS complex. And then also our ST segment, which is this little straightaway here right after our QRS complex. And then in our picture, you can see that our ventricles here have completely depolarized. So they're all red and they have contracted. Now we have ventricular repolarization, which is happening from the apex towards the base. And that's what's happening during our T wave, which is the last little bump all the way to the right-hand side of that trace. And then finally, we have ventricular repolarization complete. My ventricles here are all green, and that's going to be the straight segment of our ECG that happens after our T wave. And so this is our ECG trace. All right. So the electrical activity of the heart is going to cause not just, a switching of ions, it's going to cause contraction and relaxation of the cardiomyocytes. And so one full cycle of this, like when the atria contract and then they relax and the ventricles contract and they relax, well, that's called one cardiac cycle. It may interest you to know that one cardiac cycle happens every 8/10 of a second. That is how fast this is happening. And so the picture that I have here on this slide are the various phases of the cardiac cycle, which is what we're going to go through right now. All right. Well, one thing that happens when you go to a doctor is they will listen to your heart. And one thing that they're listening for are heart sounds. Heart sounds are described as sounding like this: lubbed up, lubbed up, lubbed up. And so the lub is called S1, and like sound 1, and then the dup is called S2 for sound 2. S1 is louder and longer, while S2 is considered sharper and softer. Now, I know that an easy explanation for this is to say, oh, it's the valves as they close, but in reality, the valves are going to operate silently. What is actually causing this sounds that clinicians are listening to through the stethoscope is actually turbulence in the bloodstream. So the movements of the heart are going to kind of slosh that blood around, and they're going to knock against the valves, and that's what's going to cause the sounds. They do coordinate with valve movement, however, but the valves themselves, they're silent. Okay, so as I said, one cardiac cycle is happening every 8/10 of a second. And so what we have going on here are the different phases of our cardiac cycle. In phase number 1, we have rapid filling, which is happening because all of the chambers are relaxed. And so we have passive filling of the atria and of the ventricles. So blood is just passively entering our right atrium through the inferior and superior vena cava, and filling the right atrium is just passing right through our AV ventricle and starting to fill our ventricles. Then we have our next phase, which is atrial systole. And so you may notice that this blue box and the green box, they're under the similar heading of ventricular filling, because this is all what's happening in order to get these ventricles to fill to their maximum capacity before they contract and they eject that blood out of the chamber. And so in our green box here, we have atrial systole. So that means that the atria are contracting, and as they contract, so that's what these little lines here mean, contraction, contraction. And as they contract, they're going to force blood through our AV valves and into the ventricles. Next, we have isovolumetric contraction, which is the next phase. Iso is a prefix that means same. So what isovolumetric contraction means is that the walls of the heart are starting to contract, but not to the point where you're changing the volume of blood inside of those ventricles. And so what's happening is that the walls here are contracting, and when they contract, they are increasing the pressure inside of those ventricles. And when the pressure inside increases, they're going to push the blood back up towards the AV valve that we have here. But because of the structure of our AV valves, the pushing of the blood up on those leaflets, it's going to force those leaflets closed. So the blood cannot flow backwards into the right and left atrium. So that's what's happening here during isovolumetric contraction. Both ventricles are starting to contract. They increase the pressure inside of their chambers. That's going to push the blood back up towards those AV valves and force them to be closed. And that's going to prevent backflow of blood into the right and left atria. Number 3, we have ventricular ejection, which basically means that now we get more contraction. So you can see from these little lines here that are on our pictures, we have more contraction happening, and now we're going to push all of that blood that's been in the ventricles through our semilunar valves. So the blood is now going to go through our pulmonary semilunar valve and then into the pulmonary trunk, into the pulmonary arteries, and then out to the lungs. And it's going to push through our aortic semilunar valve, and the blood was going to go through the aorta and then out to the body. Number 4 says that we have isovolumetric relaxation. So now the walls of the ventricles are relaxing, they are repolarizing, but it's isovolumetric. So these AV valves are going to remain closed, so we haven't changed the pressure in the ventricles enough to allow for blood to move from the left atrium into the left ventricle or from the right atrium into the right ventricle. Like there's not a large enough drop of pressure in the ventricles yet in order to allow for blood in those upper chambers to open the valves and come back in. So that's what we mean by isovolumetric. It's the walls are starting to relax, but not enough to change the volume of blood that we have inside of the ventricles at this time. But then it goes all the way back over here to step one of ventricular filling. Eventually the walls are going to relax enough, the pressure is going to drop, and just the weight of the blood that is collecting in those atria are going to force those AV valves open, and you're going to get passive filling of those ventricles again. And then the whole thing starts all over. So this just happens time and time and time again. Oh, and thank goodness for that, right? Okay. Okay. And so this is just going to go through again what I talked about. So like I said, we've got rapid ventricular filling. This is going to correspond with the P wave that we have on our ECG. So when ventricular filling is almost done, that's when our P wave is going to happen. Our P wave is going to represent atrial systole. And do not worry about the EDV. Okay, as I said before, isovolumetric contraction simply means that we have no blood ejection. We are not changing the volume of our blood yet. So the ventricles are whenever the ventricles contract, we're going to start to increase the pressure inside of those chambers and decrease the volume of those chambers. And then, like I said, the blood is going to surge up and close the valves. But at this point, we have no change in the volume of blood. Then we have ventricular ejection. We're going to have very strong contraction of the ventricular walls. That's going to force the semilunar valves open. This is the part that corresponds to the plateau that I showed you, where our calcium channels are open and calcium ions are flowing into the cells. This is when our T wave is going to happen. And then the ventricles are going to expand during isovolumetric relaxation. And so our ventricles are going to relax, not enough to allow those AV valves to open yet. But this is the time when blood that is going to flow backwards in the aorta towards the semilunar valves, and also in the pulmonary trunk toward the semilunar valves. And remember, those semilunar valves have that cup-like structure. So when the blood comes in, it fills the cup and pushes it down. In the aorta, that's how our coronary circulatory system is going to receive oxygenated blood to deliver to our cardiomyocytes. So this is a really important part of the whole process. And remember that during isovolumetric relaxation, our AV valves remain closed because we haven't dropped the pressure enough inside of the ventricles to allow the weight of the blood that has collected in each atrium to push open those AV valves and start filling yet. All right, and that's all I have for you. Thank you for watching part 2, and I'll talk to you soon.